How's everybody today? Good? All right, let's start with housekeeping. What's on Friday? Quiz. It's going to be in Campus Web, just to let you know that. I've looked at both of those, and I'm going to write that in Campus Web to make it electronic. And so I'll bring, like I said, I'll bring 12 PCs to class. If you have your own you'd rather work from, you may do that. It's your choice. Okay. So anything else with that? Chapters 1 and 2. Okay. The talk that Chase gave yesterday or Monday at 4 is posted on bookmarks for your course if you would like to watch that. It's up to you if anybody would like. I put a link to it there. So we videoed it. I forgot my tripod. A student held that, so there's a little bit of motion in it. Don't get seasick. Never mind. Upstairs, there is a filing cabinet which has your graded work in it. That's not a storage cabinet. Please collect your graded work and take it with you. Okay? So we can have space for more graded work. Cool? So we're getting things back. I will probably, the first of next week, enter all the lab grades that we have returned. I have not put those in Campus Web yet, but they will show up there in about a week, at the same time that we enter your first quiz score. And so it'll be more full in terms of what I'm showing you for your returned work. So just to let you know that. Last part, labs. When we grade labs, when we read a conclusion or an answer that's identical to another one, we begin by writing a note on the papers that we find that. If this continues, we will divide the points in half between the two of you. Okay? And then if it continues after that, then we give zeros. Okay, I'm telling you this not because I don't want you to work with your lab partner, but because I want you to write your own answers. Okay? And to use your phrasing and not to copy from someone else. Okay? The same when you make your graphs. Okay? I know you're graphing the exact same material, but don't let your partner make one for you because you will never learn how to graph with Excel if you don't make your own graphs. Okay? And when you name your graph, that's where we tell if they're exactly the same or not. Well, that and the formatting all the way across them is identical. And so when they're absolutely identical, then we believe that one person has made those and we put the same comment on them. You guys understand that, don't you? Because I'm not trying to teach only your lab partner. I'm trying to teach you also. Okay? And the only way I can get you to learn how to use Excel is if you use it yourself. Okay? Did I just accuse everybody of cheating? I didn't mean to if I did. Okay? That was not my intention. Okay? So I want you to do your own work. Please do your own work. That's the way you'll grow. Right? If you don't practice playing, then you'll never learn how to play. Okay? So, cool. Is it easier to have your lab partner do it for you? Or if you're the lab partner that can do it, then could you teach your lab partner how to do it? Yeah? That'd really be helpful, okay? So that we make it a joint thing. If you're the one that does all the time, make sure that this time your lab partner does. Cool? All right, so help me with that, yeah.
On our observations,
Yeah.
someone doing them and someone writing them.
Yeah, but I still want those phrased in your own way and show show units. That's one of the biggest things I catch right now, guys, is you guys, not everybody shows units and stuff like that on their numbers. Gosh, put them on there. But they should be identical. I mean, because two different people are doing it. I would much rather you both take notes as you go, that you both participate in the experiment doing it and those types of things. Now, I realize you're doing it together and that there's overlap. So we're not targeting you for that. What we're targeting you for is blatant copying. And so that's what we're really looking for. So if you do copy your observations from someone else, then make sure that you phrase it in the way that you would say it, not the way they say it. Does that make sense? Yeah. Cool. Any other questions on that? to talk about, well, we finished on allotropes, right? And what was the definition of an allotrope? Something that has the same, right, element, but a different molecular formula. So what would be two allotropes of, I'm trying to think of something that's not on here. Phosphorus. Well, you guys don't know those, do you? P4 and P10, but yeah. So when you see that, two different arrangements of an element, then that's going to be an allotrope. So you can identify those. That's a word that we want you to know. All right, we're going to move from there to naming binary compounds. Okay, and so if I'm looking at binary compounds, what does the prefix bi mean? Two, so there's two elements involved, and there's a set of rules. Now, we're actually looking at things that are non-metals. Is that helpful to know that? And you guys can now identify non-metals on the periodic table, right? And so we can easily look up there and we can see the non-metals in that part of the periodic table and know that that's what we're naming. Cool? All right, and so then we also need to know that things can combine in different ratios, right? Well, that's one of the laws that we learned. And so if it's combined in a 1-to-1 ratio, it has a different name than when it's combined in a 2-to-1 ratio. And you guys already know this, and in fact, I think this is a good thing to look at as a model when you can't remember how to name something that has nitrogen and chlorine in it. Right, you with me? Or whatever that different combination is. To have known compounds is helpful, isn't it? Okay? Now, if I have one carbon, anybody know what the prefix is? Mono, but when it's the first element, what do we do with mono? We leave it off, don't we? So, because this is carbon, right? It's not monocarbon, it's carbon, but it actually is monocarbon. So it has no prefix. If there were two, what would it be? Dicarbon, right? So you guys catch that? So when it's more than one, I identify it. When it's one, I leave the prefix off. So it's carbon monoxide because there's one oxygen in it. It's CO2 carbon dioxide when there's two oxygens. And so those are the prefixes that we're going to use. Actually, there's a whole list of those. Yep, go ahead.
So what if that's the same ratio, the different?
So if I have C2, C2O4 or C4O8,
yeah.
So right here,
Yeah.
we use these prefixes. So when I would have 4 carbons, then I would use tetra. When I have 2, I would use di. Okay, so I would use these prefixes: mono, di, tri, tetra, penta, hexa, hepta, oct, nona, and deca, right? And so those are the ones that we use for binary covalent compounds. There's another set of prefixes that we're going to learn for hydrocarbons, okay? And those are meth, pro, but, pent, and so on. And so this isn't the only list you're going to have to learn to name compounds. Okay, this is just one of them. All right? So if I'm looking at this molecule, then how many nitrogens are there? 2. And how many oxygens? 1. Dinitrogen monoxide. And I'm going to tell you right now that your book gives this as an example, and I added to this slide, and I put this right here. Because this goes with another list that's later on in this presentation. That's the common name for it. Does anybody know what nitrous oxide is used for? Dentistry. It's laughing gas. And that's the common accepted name for it. It would be like calling water dihydrogen monoxide, which is incorrect also. Okay, because water is the common name for the molecule that is H2O. Cool? Okay? And so there's other molecules that are structurally incorrect that are common names. And I put this in this group, and your textbook did not. So, cool? Letting you know that out loud. All right. how do we name these? We first name the nonmetal, the second nonmetal, and so we have prefix plus name, and then prefix plus root plus IDE. So we put a suffix on the second element. Now, do we do that with everything that we name that has a single element in the second place? IDEs? Yeah, very often. Okay, so be aware of that when well, what's the name of the molecule, the ionic compound with sodium and chlorine? Sodium chloride. So that same suffix is used in that relationship of metals and nonmetals. So there's a lap over there, right? Just let you know that. Now, if I start adding oxygens and those types of things, then there's a whole nother nomenclature system that comes in, and we'll use that with polyatomic ions, and those are eights and ites, okay, for those suffixes. And then we can do that for other elements also. But anyway, but binary covalent, so we work on that. This is showing the nitrogen, right, dinitrogen monoxide in that step-by-step process to get there. All right, so name the compounds whose molecules contain the following elements: 1 atom of silicon and 4 atoms of chlorine. So first write the formula, okay? Write the formula. I think that's always easiest to me to start there. So that first one is SiCl4, right? And so how do we name the first element? Silicon, right? And is there a mono in front of that? No, it's dropped, right? So silicon tetrachloride, okay? So write these down. Then what about the next one? 1 atom of sulfur and 3 atoms of oxygen, SO3. Sulfur trioxide, okay? 1 sulfur and 2 bromines. Two bromines. I put 3 on it. I made the wrong compound. Sulfur dibromide, you guys agree with that? Yeah, and what about the last one? 2 atoms of phosphorus and 3 atoms of sulfur. So P2S3, P2S3, diphosphorus trisulfide. Yeah. Now, the more electropositive element goes on the left, the more electronegative element goes on the right, but that takes a whole nother knowledge of the periodic table we haven't got to yet, right? And so the more left, right, and the more down, more electropositive, generally, the more right and up, the more electronegative. Till we get to this row, and what do we know about them? They're neutral in a sense, yeah. So they have a full shell of electrons, and so they aren't wanting electrons or wanting to give them away. Okay, cool? All right. So silicon tetrachloride, sulfur trioxide, sulfur dibromide, and diphosphorus trisulfide. Okay, so we did all right there. How about these? You guys want to give them all a shot? They are all nonmetals, right? Because at some point we're going to get a list and it's going to have different types of molecules in it, right? So you're going to have to identify the type. So just be aware of that. That's coming. All right. Nitrogen triiodide. First one. All right, go ahead. You guys write them down. Name them. See how you do. There's one on there that everybody might or might not know, and that's A little s. Anybody know the name of that? Arsenic. Okay? Arsenic. People are still writing out these teeth. This is good practice, isn't it? Safe. Most everybody's done writing, most everybody, not everybody. So we'll pull them up. Nitrogen triiodide, nitrogen monoxide, dinitrogen tetroxide, arsenic pentoxide, carbon tetrabromide, and tetrasulfur tetranitride. Yeah? Good? How about write the formulas from the names? Because that's the next step, isn't it?
Bless you.
Are we there? All right. First one N2O5. Second one B2O3. And the third one is ClO2. Okay, ClO2. Now, I want to ask a quick question. I'm going to put an ion on the board. And I'm going to name, well, you guys already did this one, SO3 2-. And this is something that I want to make very clear, and this isn't the first time, this is a preview for when we get there. Okay? And the reason I put this one up there is because it looks similar to this. Would you guys agree with that? Is it the same thing?
No.
Absolutely not. They are chemically different, they behave differently, they are different molecules. Okay? And this one is named what? Sulfur trioxide. You know how to name this one, right? This one we're going to learn, we're going to memorize. This is sulfite. Right? Sulfite. Alright? If I had one more oxygen, then it would be sulfate. Have you guys ever heard of sulfate? Right? And that would be SO4. Okay? Cool? You guys with me? So those are completely different. They have different names, but students confuse those sometimes. Okay? And when you're naming things, then you need to identify when I have a polyatomic ion versus when I have a binary compound. Cool? Are there other examples of this? Yeah, what if I had NO3 versus NO3 minus? What's this one called? Nitrogen trioxide, and it's a binary compound, right? This one is called nitrate ion, right? And so it is different than the binary compound, okay? And in fact, this would combine with a cation to make a salt. And salts are named differently. Okay, cool? Yep. Hopefully that's helpful, right? That's a preview. We'll get there. This is showing some binary compound, talking about binary compounds of hydrogen. And these compounds are named using different systems. Many are named for acids, okay? So if I have, well, this is kind of funny, all right? We have name changes. If I have HCl gas, it has one name. What's its name? Hydrogen chloride. Okay, so it uses kind of the binary system, right? But if I make this HCl aqueous, what do I have? I have hydrochloric acid. Okay, so it changes names depending on what phase it's in. And that's kind of scary, isn't it? Right? We'll try to teach you those things, okay? And how to name things based on what it is. And there aren't very many of those, so they're easy to learn. Cool? Or that we're going to use in this class. Now, those that are not acids are sometimes given special names. Like NH3 is called ammonia instead of nitrogen trihydride. Okay, you guys with me? So that's called ammonia. Phosphine is pH3. Arsine is ASH3. And I added this one to this list. It's not one of the hydrogen compounds, but I want you to know that it's named differently. It has a common name. Okay? And so that's the accepted name as nitrous oxide. Now maybe chemists are trying to change that around the world, but that's what it is if you go to buy it. Cool? All right. Excuse me. Formulas for ionic compounds. Ions. You guys know what cations and anions are, right? And if you're having struggles remembering that, I always look at it from either one perspective or another, right? And if I have a cation, right, there's a plus sign in the name. Cool? If I don't remember that, then there's an anion, right? And that has the prefix "an," which is like the Antichrist, and that's easy to remember that that's negative. You'll never forget that one now, will you? Okay? So, didn't see it coming. All right. Caught you off guard. All right, "and" is negative, "cat" is positive. Single atoms that gain and lose electrons form monatomic ions, right? And so when we gain and lose things, then we can make binary ionic compounds. Okay, there's a nice example that you know. And so the cation is Na plus, the anion is Cl minus, and when I put those together, then I have NaCl, and I name that. What's its name? Sodium chloride. I named the metal first. Sodium, right? And the anion, or non-metal, becomes chlor with the suffix IDE. So you guys know how to do that. And this is talking about electrons transferring and those types of things. But, yeah, we'll get there. Now, elements. This is a partial periodic table, and it's showing most of the elements that we're going to use for this course. Okay, and we'll use a few more. Cool? All right? But what it's showing us is their common oxidation states. Okay, cool? And so if I'm looking at family 1, then what do I notice all the way down through there? All plus 1, but hydrogen, and hydrogen can be positive or negative. Wow, that messes with you, doesn't it? Depends on what it's combined with. Cool? All right. Now, if I'm looking at the second family, then what are those? They're +2s. Okay? Now, I'm going to skip all of these in between except for those gold ones. You see the gold ones? Or yellow, whatever color. What color is that? Gold good? Tan? Gold? Tennessee orange? Tennessee orange. Okay, we'll call it Tennessee orange. All right, so if I'm looking at that, then what do you notice about these four elements? They only have one common oxidation state. Okay, so those are the common oxidation state, they only have one. And so it's good to know those. Okay, because they're named differently than these that have multiple oxidation states. Cool? You guys with me? There's a different way of naming those, so you need to know those. All right, now, if you make a mistake because silver, zinc, and cadmium are transition metals and you put the numbering in there, I will mark it as wrong, but I'll give you the points. How's that? At least first time through. Cool? Okay? So, now, aluminum is always +3. Okay? Now look at these over here. What do you notice about them? They all have one oxidation number and they're all negative, right? So you're combining negatives over here with positives over here, and those are making what? Binary ionic compounds, or ionic compounds. Cool? All right. So here we go. Taking aluminum. Aluminum we combine with chlorine. Right? When we combine aluminum with chlorine, if aluminum is always +3, right? Al +3, and we want to make a binary compound which has a charge of 0, how many chlorines is it going to take? 3. So 3 Cl minus 1s, because Cl is always -1, and so those combine as AlCl3, aluminum. What's the name of it? Aluminum. Nope, nope. Nope. Was there a mono in front of this name? Aluminum chloride. It's just aluminum chloride. That's it. You guys, there's no prefixes on binary ionic compounds. It's just the cation name and then the anion with an IDE suffix. Okay? Is that confusing or what? Mm-hmm. Yep. So you have to be able to identify when it's a cation and anion, or when it's two nonmetals, okay, in a binary molecular compound or covalent compound. Yep.
So does that only happen for the binary ionic compound?
Yeah, that form of the naming. So let's try another one. Okay? Let's try another one. Well, we'll get there with names here in a second. This is actually just showing you how to put them together. Okay? Let's make a compound with aluminum and oxygen. Okay? Let's make a compound with aluminum and oxygen. That's what's on the next slide. So, without me showing it to you, let's build it. Now, we already know that aluminum is our cation, and it's +3, right? What about oxygen? It's always -2, so oxygen is -2, or you could write 2-. I switch back and forth between two systems because some textbooks use one, some use the other. It means the same thing to me. Okay? So I move back and forth just to let you know that. Now, can I teach you a little trick on this right now? Yes? No? Okay, so if I can identify what the ions are, if I lasso that and pull that there and lasso that and pull that down there, then that's going to be the formula. Okay? Because that ratios the charges. Well, so that means this is Al2O3. Would you guys agree with that? Now, what I am doing is 3 times -2 equals what? 3 times negative 2 equals negative 6, and 2 times plus 3 equals plus 6, and plus 6, right? Plus a minus 6 equals 0, and that's the charge for the compound, right? You guys with me? So that's what I did, was I actually did 2 times plus 3 plus 2 times, 3 times minus 2, okay? Plus 6 minus 6 equals 0, based on the charges. Yeah, shortcut, right? Good shortcut? Yeah. So this is showing the same thing here for aluminum oxide on the board, multiples of. All right, you guys make the formulas for combinations of sodium and bromine, barium, and fluorine, lead 4, not lead 2, okay? Lead 4 and oxygen, and then calcium and oxygen. You guys see if you can write the ionic compounds that would happen from that. So what did I do on the board? I didn't write the compounds yet, did I? What did I do instead? I started with the ions, didn't I? The cation list and the anion list, and then I'm going to combine them after I do the anions. I do this until I learn how to do this, and when I learn how to do this, then does it become easier? And I can just look at them and combine them and write them? That's what happens, okay? But to start with, I think it's easier to do that, and so then if I'm looking at this and I have each with a positive and negative charge, so this one's easy. What is it? NaBr, right? And what would I name this? Sodium bromide. Okay? Now, what about this one? So if I have 1 Ba and 2 fluorines, BaF2, and this would be, what's the name? Barium fluoride, right? Not dye. Do not use dye. This is barium fluoride. Okay? This next one, well, we haven't got to how to do this yet, but I'm going to show it to you anyway right here. What's the combination? So when you see that 4 lead and 2, what do you notice? Those are multiples of each other. PbO2, I would reduce that to the lowest whole number ratio, unless there's a reason why I wouldn't. In ionic compounds, that's seldom the case. Yep. You could, I guess. I would do it this way, is I would say I need 2 times minus 2 to make a plus 4. That's the way my brain works. Okay, so then that would be 1 to 2. Okay, does that make sense? That's the way I would do it. So that, like I said, that's a shortcut, but it didn't work there, did it? Okay? Now, I'm going to ask what the name is, and I'm going to tell you it's wrong. Unless somebody in here has had a good high school chemistry teacher, and they'll spit that out just like no problem. What's the name of that? Lead oxide. Is that correct? No, because what's missing in that? Let's go back to our slide right now and find lead on the periodic table. What are the 2 oxidation states that are common? +2 and +4. So I need to be able to tell the chemist, right, that it's lead 4. And so when I write the name of this, then I would write lead in parentheses lead 4 oxide. Cool? So you have to learn your own numerals too. Sorry. Yeah, lead 4 oxide. Cool? All right. What about that last one? Calcium and oxygen? CaO, and what's the name of it? Calcium oxide, because calcium only has 1 oxidation state. Now, do you guys see why I said to learn the ones that have a single oxidation state, because you don't have to write the Roman numeral with those? Cool? You guys got it? That's why. All right. Now we actually get to do the section on this.
What about mercury?
HG.
It just has a 2 close on there on that chart. That's what it said. Just curious about those 2.
It's not given as one of those that we don't have to identify. I'm not sure on mercury. Mercury's weird. It actually commonly exists as a dimer, 2 of them together in many, many compounds. And so it doesn't make the formula ratios that you would expect. And so it does some weird things, okay? So that may be why it's not put into that group. I don't know the answer to that, so I'll say I have limited knowledge there. Yeah, I just know the ones that are shown in Tennessee orange are the ones that we know to be exceptions, okay? So, outside of those first 2 families. All right. So using formula and charges to determine charge of an ion. Oh, yeah. So FeCl2 and FeCl3. Are those the same compounds? They're both iron chlorides. Would you guys agree with that statement? Yes? But they're different because there's a different ratio in those binary ionic compounds. And because of that, these are going to have 2 different names, aren't they? Can you figure out what those numbers should be on the iron ion so you can name it from that combination? We don't know what the iron is. It could be either +2 or +3. It becomes obvious when I say that which is which, right? But we know that Cl is always what? Always -1. And so if I have 2 times -1, then that equals -2. Would you guys agree with that statement? So to make this overall 0 charge, then what does the iron have to be? It has to be +2, right? Yeah. So the iron is +2, so when I name that, then that is iron 2 oxide. Cool? Oh, chloride. Yes. Not what I wrote, but what's on the board, yes. I don't know where I got to that. So, weird things happen in my brain sometimes. Okay, so cross-wire occasionally. All right, what about the next one then? Same logic, what's the iron's charge here? There's 3 Cl, so there's 3 times -1, so that's a total of -3, so the iron has to be +3, and so when I name this, all right, you guys name it. Cool? Yeah? All right. So, what is the charge on the cation copper on the molecule on the board? What is the ion? What is the copper ion, the cation in that compound? What's its charge? So you're thinking it's +1. So that name of that compound would be copper 1 oxide. How many people agree with that? I do. Yeah? Yes? No? What's oxygen? Which family is it in? It's in 16, right? 17 is minus 1, 16 is minus 2 when it makes an ion. And so the oxygen up there in Cu2O, right? The oxygen is 1 times minus 2, right? And then I'm going to do the math. I'm going to show you guys how you do this algebraically. Is that okay? So plus 2 times x equals, what's the charge overall? It's 0, isn't it? So this algebraic expression is going to be equal to 0. Cool? You guys with me? And so that means this term is negative 2 plus 2 times x. So is, or 2x is equal to 0. So then if what do I do next? Do what? Add 2 on both sides. So we make this plus 2. And we get rid of that. And now we've got 2x. So then what are we going to do? Divide both sides by 2. And so x equals 1 or plus 1. You guys see that? That's the way you would do it algebraically. Now, those numbers and ratios, can you do them in your brain? Yeah. Okay. Do you sometimes make a mistake? Yeah. Okay. If you want to make sure you get it right, do it algebraically. Okay. Cool. All right. What about the next one? Using that same logic. Copper has a charge of plus 2, right? So the first one is Cu plus 1, the second one is Cu plus 2. So when I name that first one, that would be copper 1 oxide. When I name the second one, it would be copper 2 oxide. Cool? Now, we used to use an older naming system, cupric and cuprous. Okay? Yeah, I'm glad those are gone. There's no confusion here. Okay? So, yeah. All right, now, I've talked about these already. I've put a couple examples on the board of polyatomic ions. Okay? I previewed this, and I put nitrate on the board, and I put sulfite on the board. Okay? And now we have some other examples up here, and carbonate is one of those. CO3, 2 minus. Okay? And it's 1 carbon atom bonded to 3 oxygen atoms. Okay? Now, we could calculate charges on these, but they're perceived charges. Okay? And in fact, we'll ultimately learn to do things like calculate formal charge and so on, which is a representation of what elements are. But at this point, I just want you guys to memorize the polyatomic ions. Okay, and I'm going to give you a list of those sooner or later, and we'll work on that stuff when we get to the chapters that cover it. Okay, cool? All right, so ammonium ion in H4 has 1 nitrogen and 4 hydrogen atoms. It has lost 1 electron for a +1 charge. And so anyway, most polyatomic ions are cations. The nitrogen ones, like we see with ammonia, are the common positive ones. Okay, so nitrogen is the common ones. And so this gives that one example of the ammonium ion. I can have other configurations which would have that positive charge. In fact, you'll see that a lot in organic chemistry with nitrogenous structures. Okay, and so there becomes an acidic proton that can attach and detach. In fact, anybody ever heard of an amino acid? Oh my gosh. So I have been asked by my students here in the back who come in and who are cackling to pull the fire alarm at 2:13 because they have a genetics test and they think that they could get out of it if I pulled the fire alarm. What do you guys think? This is on video and going public. I won't mention names of my students back there, but So, it's not gonna happen. Have good luck with your test, ladies. I hope you do well. So, a little bit of side entertainment there. So we're looking at the ammonium ion, and so that is the structure of that, the acetate ion. And I like to draw that. Well, we'll do that a little bit later because I'm about out of time. But anyway, bromate, carbonate, chlorate, cyanide, hydroxide, nitrate, phosphate, and sulfate. Those are common polyatomic ions. I'm going to give you a little bit bigger list that I'm going to get you to memorize, but that's a good beginning, right? So to start looking at them. All right. So anyway, writing formulas of ionic compounds with polyatomic ions. So not only is it important to know their name, what else is it important to know about them? Their charge. You have to memorize the name and the charge. Sometimes it's easier to remember a compound that you know that involves that polyatomic ion. Does that make sense? And so knowing that sodium nitrate is a 1-to-1 combination, then that tells you that the nitrate is always -1 because sodium is always +1. Or if you're on a test and you can't remember the charge on a polyatomic ion, and I've used it somewhere else in the test with something that's not variable, can you look at that and determine the charge of the polyatomic ion? And the answer is yes, okay? Use your chemistry knowledge to help you when you're in trouble, okay? All right, so this is showing an example of a polyatomic ion and a cation, and notice the cation is +2, this is a -1, right? And so you guys have seen this before. This is calcium nitrate, and it's written as CaNO3 Now, the way they have written right there is wrong. What's wrong with that? Have they got a negative charge in there? That's wrong. Okay? It should be written how? CaNO3 with no negative charge showing. You guys see that? If you're going to show charges, you want to know that this is -1. I would rather you write it up above that just so you're acknowledging that the nitrate is -1. And at the same time, what should I do for the calcium? Write it way up above where it's not on the molecule itself. Have you noticed when I make them 0, what I do? I put them in square brackets, and then I write the 0 on the outside of that square brackets because I want you to know that I'm referring to the whole molecule when I'm writing that 0. Okay? Or if I change this compound, I'm going to change it to CaNO3, right? And I put square brackets around that. What would I write on the outside of those square brackets? The calcium is +2. This is -1. I would write a +1 because that plus isn't accounted for in the combination, and so I need to tell the person who's looking at this is a +1 ion. You guys with me? Okay, really important. Those charges just can't be thrown around. Okay, you need to account for them. That's how we know the right combinations. And so if it's still charged after I combined it, then that's incorrect. Okay, I didn't catch that when I was reviewing these slides. I'm going to fix that. Okay, so cool? Yeah. Good teaching. Maybe I should leave it for the next one.
Is that the next slide?
Yep.